looking forward to. So welcome to another lovely Math 211 lecture. We are now, I think, in week 12, which would make this lecture 23, although, no, we missed a day, so maybe 22. I don't know, whatever lecture it is November 16th. And we are going to be doing today a new chapter, and that is chapter 19 on sampling methods and sampling distributions. A really, really important idea. And this section is somewhat qualitative in nature. It's not very mathematical, but the chapters that are going to come after this will rely on it. What was that question?
Yeah, we're not doing chapter 18, right?
That's correct. We're skipping it.
Okay, great. Thank you.
All right, until 19. So if you want to know if your soup has enough salt, you don't have to eat all of it. You only have to taste a spoonful, right? You put your spoon in, put a little taste, and this gives you the idea of whether or not the bowl is ready. And even if it's a big bowl like the one shown there, although I'm not even sure I can finish that in any given sitting, it'll be a good challenge though. Even in a situation like that, if you stir it and you take a small little spoon, it's good enough. In other words, you don't need a larger spoon because the bowl is so large. As we're going to see, a sufficiently sized sample doesn't need to get larger when the population gets larger. So the idea of inferring something about the entire population from a knowledge of a small portion of the population, this is really the heart of statistics. So, anytime there's a poll where it says, this candidate leads this candidate by this percent, or this one has that percent chance of winning, or 86% of people believe in aliens, or whatever the case may be. When you come across a stat like that, and you say to yourself, wait a second, nobody ever asked me, how do they know that it's accurate? It's because they're taking a sample and they are trying to infer something about the entire population from that sample. People who are not statistically inclined say, well, they didn't ask me, so they don't know what they're talking about. But people who are mathematically and statistically inclined know that the rules of probability and the rules of statistics allow us to come up with very, very, very reliable estimates based upon a sample. So statistical inference, which is the heart of statistics and the heart of this chapter, statistical inference, allows us to make conclusions about a population based upon a sample. So if you want to use 1,000 likely voters to tell you about all likely voters, we got to make sure we pick the 1,000 in the right way. I cannot go outside of a Trump rally or a Biden rally and then ask 1,000 people, hey, who do you think is going to win, to get a reliable prediction? Because in both cases, whether it's for the first or for the second, the voters are going to be biased in one direction over the other. So making sure that your sample is a reliable sample is not as easy as it sounds, but a lot of times you kind of know when it's bad. So suppose I was interested in people's favorite sport. I'm curious about people in CSUN, what their favorite sport is. Or better yet, people in Los Angeles, what's your favorite sport? So if I asked you guys, hey, everyone, put in the chat what your favorite sport is. Go ahead right now. Put in chat what your favorite sport is. So let's see, what do I have here? What do we got? Football, baseball, basketball, baseball, football, soccer. Well, of course, you play soccer. That makes sense. Let's see what else we got. Football, volleyball, track and field, football, MMA. Boom, MMA. Yeah. That's okay. Water polo. I used to play water polo, but then my horse drowned. What else? What else we got? Okay, your favorite sport is not really water polo, is it? Alex, hello, Earth to Alex.
I was typing, but I was almost on a team in high school. I spent like a lot of time practicing water polo.
Really?
Yep.
Alex is always the wild card. Yeah, outlier. Let's use statistical terms. Well, unfortunately, all of your choices are wrong. We all know that the best sport is golf. I mean, that just goes without saying. But anyways, I will assume that when you all wrote your answers, it was because the obvious best sport in the world is golf. So you all picked the second best sport, which is fine. Let's assume that was the question. Now, this is a nice sample. Is there any reason why you would think that this particular class, the people that I just asked, my 211 math class, are more inclined to like one sport over another? If CSUN was a school, to a baseball school, in other words, everyone who came here had to play baseball, and you had your aspirations were to play baseball professionally, then it would probably be biased somewhat towards baseball. If I went to the Lakers game tonight or tomorrow night, whenever they're playing, and I asked 1,000 people, "Hey, what's your favorite sport?" Do you think that will be a good way of determining a sample for all of Los Angeles?
No.
Going to a lake, why not? What's wrong? There's people from all over the place. What's wrong with that?
Because they're all there to watch a basketball game. It's
Yeah.
not really random.
Exactly. They're all there to watch a basketball game. It might not be their favorite sport, but chances are that there might be a tendency for people there to like basketball more, so it's going to be a little biased. So when it comes to sampling, one of the main goals is to make sure that it's not biased. And the way of doing that is to randomize. You let chance choose the sample. You don't do it yourself. And there's different ways of getting a random sample. Some better than others. And as we go through the lesson today, we'll see some of the ideas. But one of the main ideas of picking a valid sample is to make sure that it's a random sample. So here are some terms that are used a lot when it comes to sampling. Okay, someone say, "Oh, Addison, good to see you. You know, the class is just not the same without you." So at the end of the class, make sure I get you down for being late, but I don't want to interrupt the flow. So vocabulary of sampling. We have the population. This is the collection of people or objects that you care about. A population does not have to be people. If I'm interested in the favorite sport of people in Los Angeles, then sure, the population is the people of Los Angeles. If I'm interested in the average miles per gallon of cars on the road, my population will be the cars. So in general, the population are the objects that you're curious about. The units or the different cases are the individuals in the population. You might have heard the term a case study. We're studying specific cases. So that car, that TV, that book, that person, etc. Those are the units. Now, the population will have a given size, the number of units in the population. Sometimes you know the size of the population, sometimes you don't. If I'm interested in the average weight of a grain of sand on Earth, my population would be all the grains of sand. Do I know how many grains of sand there are?
No.
No. So you might not always know the population. Maybe Alex, there's Alex being Alex again, classic Alex. So Alex, can you explain how you would know the number of grains of sand on Earth? I'm just curious. And don't type. We all want to hear your voice.
You could estimate by a certain area. gathering-
Estimate, wait, estimate, you mean use statistics to determine? Is that what you mean?
That's exactly what I mean.
What? And yes, you could, but even if you did that, you would not know the exact value. Right? Spoiler alert, the answer is yes. Okay, so you cannot know the exact population, but you are right. I could approximate, and I can use statistics to do that in ways that we might even see. Now, parameter. A parameter is some number that is associated with the population. Some of the most common parameters that are used in practice are the average of the population, the standard deviation of the population, or the median of the population, or the maximum value of the population, or the minimum value of the population. But a parameter, by its very definition, is something that refers to the entire population. Now, if I wanted to actually ask everybody in the population, or check every car on the road, or every book in existence, then I would be taking a census. Now, the government takes a census. Anyone know how often the government takes a census?
Every 10 years.
Every 10 years. It's actually a federal crime to lie on the census. So the census is really important. And the idea of the census, even though it's not perfect because there's a lot of homeless people, for example, that you can't necessarily ask, but for the most part, the idea of the census is to ask everybody in the country some questions so that we know the exact values. And we can dictate government policy based upon what we have. For example, if we see that, a significantly high percentage of the population wants something or needs better roads or needs some kind of infrastructure or whatever the case may be, we can use that for the government to enact policy, which it does. Whether the policy is good or bad, that's a whole nother question. Now, if you do take a census, great, but usually we don't ask everyone because it takes too much time and it's too much effort and too much work. A government can do it, but we can't. If I'm curious the average height of every American, I cannot conceivably contact every American and get this value. Even if I could, by the time I was done, people would have died, people would have been born, people would have grown. So it takes time. So what do? I take a sample. The sample are the units that you're actually studying. And the sample is relatively small, hundreds or thousands usually. And of course, what's the sample size? We usually use a lowercase n for the sample size versus capital N for the parameter, for the population size. Very rarely do we use the population size in formulas because we don't often know it. But our sample size, we take a sample, so we can get that. And then what do? We take our sample and we form an estimate. This estimate is designed to guess what that parameter is. Oh, we don't know the average of the population? No problem. Take our sample and we will use a sample average to estimate the true average. I don't know the tallest person on the planet. Okay, so I will take a sample and I'll use the tallest of my sample to estimate the tallest on the planet. Oh, I don't know the average miles per gallon of every car on the road. No problem. I'll take a sample and I'll take the average of my sample to estimate the true value. Oh, I don't know how many grains of sand there are on Earth. No problem. I know how many beaches there are. I know what the square area of each beach is. I know the depth of the sand at each beach. I know the average weight of the sand at each beach. So somehow I'll do some mathematical calculations and I will use these averages to get an estimate for the true value of the number of grains of sand. Okay, so statistics is about quite often estimating parameters. And usually what's going to happen, our estimate is not going to be equal to the true value unless we're exceedingly lucky. So we will have some sampling error. Now, when you hear the term error, we usually think of it as a mistake. But it's not really a mistake. It's just your value that you got by your perfectly valid technique, just by the very nature of reality, just does not give the true value. And therefore we are off a little bit, or maybe even a lot. So the sampling error is by definition, your value minus the true value. It's the estimate minus the parameter. We don't often know the parameter. If I knew the parameter, why are we estimating it? Why spend the time and money to get a sample for a value if I know the value? So the sampling error is more of an abstract idea than a concrete value. Does that make sense? So far?
Makes
Yeah.
sense.
Okay. So here's an example. Skittles company, whatever company makes Skittles, I don't know, Skittles Are Us, says that 20% of all Skittles are red. That is their claim. So I happen to have this random sample of Skittles. I didn't get them from someone who hates reds or anything like that. I have this random sample of Skittles, and it turns out that 3 of them in my sample happen to be red. So first, what is the population in this particular problem?
The Skittles.
Every Skittle in existence. I can even go one step further. Every Skittle ever made is better because I can't speak for the rest of you, but I have personally consumed many Skittles in my life. And I would like all those Skittles to still be on the record in terms of if we want the true value, we would need to use every Skittle ever made, right? So the population is every Skittle ever made or that's in existence. Make sense?
Yeah.
Okay, question 2. What are the units? Or what is a unit? The units are 1 Skittle. Yes, a Skittle, correct. Every Skittle is a unit. You know, I never really said Skittle before without the S. Skittles. I have no problem saying that word, but when I hear the word Skittle, it just sounds weird. Is it just me? A Skittle? Doesn't sound like it should be a word. What is Skittles? What should Skittle be?
I didn't think much on it, but now you made me think on it.
Yeah, right. I mean, Skittles. We know what Skittles are, but a Skittle. It's like, would you like a Skittle? It just doesn't sound like. Would you like a Kit Kat? That sounds fine. Would you like many Kit Kats? Yes, I would love many Kit Kats, but a Skittle. Anyway, sorry, this didn't keep you up at night. I don't know about you, but it's like. Anyways, okay. So, what is the population size here? What's the population size? Dumb question. My brain had two. Yes, exactly. Exactly. I can't sleep. Right. So what is the population size? The population size is a lot. I don't even know why they're asking this. How can you possibly determine the population size? I don't know. It's big. There's lots of them. What is the value of the parameter in this example? What is the value of the parameter in this example? This we do know, by the way.
Is it the 13 pictured Skittles?
It is not, because remember, a parameter does not come from your sample. A parameter comes from the population. So the 13 pictured Skittles, that's your sample. But the parameter doesn't care about your sample. The parameter is something about the entire population. In this case, it's 20%. It's the true value of the number or the percentage of all Skittles in the world. 20% of all Skittles are red. The parameter is 20%. And we are taking at face value that when they say 20% of Skittles are red, that is an accurate statement. If I wanted to question that, if the Skittles R Us company said hey, we make 20% of Skittles red, I might want to question that and say, you know what? I don't agree with you. I will take a sample and I will infer from my sample whether or not I agree with you. That's called hypothesis testing, and that is the subject of a chapter a few chapters away from now. But for now, the value of the parameter is 20%. The sample are the Skittles in that picture.
Okay, so that will be 13.
Well, that's the sample size.
Oh, okay, that's a
Right,
sample.
the size is 13. The sample are the actual,
Red ones?
no, the sample's the entire sample,
Oh, okay.
right? All of them.
So the sample is what?
Is those 13 Skittles,
Oh, okay.
right? You know, the 13 Skittles that are making me really craving for Skittles right now. It's amazing the power of a full color picture. All right. Do you think Grubhub delivers Skittles? I'll figure it out later. Anyways. All right. What is the estimate of the parameter? That's the question. What is the estimate of the parameter? We're going to use the sample to estimate the parameter. Petition for the professor to buy Skittles. I think it's a good idea. I think it's a good idea. Skittles are, I mean, not my favorite. They're probably like, you know,
Are you sure they're not your number one?
top 20. Oh, no, they're surely not my number one. I mean, I can think of at least, you know, things that like, if you would offer me this or that, I would pick over Skittles. What's a number one? That's a tough one. Number one. I mean, I go to, huh?
What's top 5?
Okay, well, Rolos are certainly up there. I'm a big Rolos fan. And Twix is great. And I like Kit Kats. I like 100 grand. You can't really find many 100 grands these days, but I always like the 100 grand. And yeah, those are good. Oh, and yeah, and, the blue Nestle Crunch thing. That's a good one. So,
You're a chocolate fan.
well, that's a funny thing. Like I like this kind of chocolate, but if you offer me like a just chocolate like cream or frosting or cake, I'm not really a big fan of that. See, Lindsay knows 100 grams are superior. That's what I'm talking about. Lindsay knows. Yeah. But the best food in the world, if I had to pick, if I was ever, actually, one day I'm on death row and I get my last meal, there's no question I am going for orange creamsicles. Okay, there's no question. Orange creamsicles are the best tasting food on the planet. I don't know. It's you know, it's one day. You never know. You never know. But if I ever had a last meal, I am definitely going for orange creamsicles, which, by the way, are always in season. They're always in season, which is a great thing. And if you've never had an orange creamsicle, by the way, just so you know, you are missing out. OMG. Okay, they are amazing. Sorry, I go from tangent sometime. Okay, anyways, so what is the estimate of the parameter here? What is the estimate of the parameter? From our sample, if you didn't know that it was 20%, if all you had to go on was the sample, what would you say is the proportion of all Skittles that are red?
23%, because it's 3 out of 13.
Okay, so 3 out of 13, which, yeah, is that 23%? I didn't do the math.
It's 0.23 and then a whole bunch of other numbers. But
Okay, so roughly 23%. If all you had to go on was your sample, you would say, well, I have 13 Skittles and 3 of them are red, so it looks like 3 over 13, which is about 20%. It's 23%. So what is the sampling error? It is the estimate minus the true value. So what's the sampling error in this case? Approximately
3%.
roughly 3%. Make sense so far?
Yeah.
And before we go on, just because we were talking about it, so who here has never had orange creamsicles? Like never tasted The single grade. Oh my God, guys. Guys. What? Oh my God. I should just end class now and just say, go and get them. They're that good.
They used to give them to us in school.
They're so good. No, all I want is orange cream.
Babe, you like chocolate? How you had the UFOs that they can't like they stopped making them?
Sorry, I don't believe in UFOs.
The ice cream sandwiches.
I have not, but I'm intrigued.
They stopped making them though.
Well, then why bring it up?
Well, because I thought you would.
Hold on. Okay.
Yeah,
Elizabeth,
see, they were
Hold on.
delicious, but they stopped making them.
well, I've
You
never heard
would've
of them.
loved them.
I've never heard of them, but just so you know, it doesn't taste like an orange. They're called orange creamsicles, I know, but they don't taste like oranges.
They're more
Okay.
creamy. They're more creamy.
They're very creamy.
The word orange itself just pulls me away from them.
No,
And I thought
no,
they were-
come back, come back.
I thought they tasted like orange. That's why I've never been tempted to pick them up.
Oh my God, you have to. Oh, I can't even describe it.
Okay.
Oh my God.
Maybe
stop,
I'll
stop,
try them
stop,
now then, because.
stop.
But if I get even a little taste of orange, I'm throwing the whole box away.
Fine, fair. And then you can bill me for it.
Okay.
I will reimburse you.
This is recorded, just
Yes,
like.
this is just be on YouTube, so you can never deny that it happened.
Okay,
And
I'll try them for
Odalise-
sure though.
Odalise, you just failed the class, just so you know. You can leave, you don't have to come back, you got an F. So just so you know. There are other flavors too, aren't there? Like, I don't know about that, but okay, next. A poll of 1,002 California registered voters selected at random from the list of all 17.717936 million registered voters found that 55% favored legalization of marijuana. Of course, this was 5 years ago, so it's probably higher now. In the election, 57.1% voted to legalize marijuana. Describe these terms for this situation. What is the population here? I'm not looking for a number. I'm looking for the population itself. What is the population for this problem? The California registered voters. Lovely. And what are the units for this problem? A single voter. Okay, from California. Lovely. What is the population size for this problem?
The amount of registered voters?
Well, it's so no, so I mean it's not 1,002. It's the actual population size. How many California registered voters are there? There's 17 million, whatever, right? The population size is everyone, not just the people that I asked. Right? Do we agree?
Yeah.
Yeah.
Right? 17. Well, yes, the sample are the 1,002 people that I actually talked to. So let's skip parameter and census for a second. Let's go to sample. The sample are the 1,002 California registered voters that I polled. That's my sample. Of course, the sample size is then 1,002. So it says it's asking for it says the word census there. And I don't really understand what that means because this is not a census. We didn't ask everyone. So I don't really, you can ignore this. I don't really see how this plays a role in this problem.
I have a question about the sample. So you said the sample size is 1,002. So then the sample is,
Well, the sample are the 1,002 California voters that I actually polled.
so sample and sample size is the same thing, no?
Well, the sample size is a number and the sample are the objects.
Okay.
So the sample are the people. And the sample size is how many people. So they're certainly connected. But one's a number and one is the actual objects themselves. Does that make sense?
The sample was the registered voters that you asked. That's what
Yeah,
you-
they're the ones
Okay.
that I pulled, exactly.
Okay.
They're the people that I pulled.
For the other one, it was the Skittles that you counted. or
Yes, the sample then was the 13 Skittles that I had. Well, it was the Skittles that I had in my hands, and the
Mhm.
size of that sample was 13.
Perfect.
Okay.
So what did we say the parameter was?
Well, I'll hold off on that for a second.
Yeah.
The estimates is what I get from my sample. And my poll gave me an estimate of 0.55, 55%. Now the parameter is what I get from everyone. It's the actual true value. Now, I don't know the actual true value, but the problem is insinuating that the true value should be 0.571, 57.1%. Why is this not really 100% accurate? Why is that not truly the parameter? Because just because people are registered to vote doesn't mean they actually vote. So the 57.1% who voted, yeah, exactly, Tyra, right? Not everyone who is registered voted. But let's pretend it's a perfect world where everyone votes. And therefore, it is truly a parameter. Let's just go with it for the sake of the problem. What therefore would be the sampling error? How would I calculate that? Orange Fanta. Gotta love it. So what will be the sampling error? 0.55 minus 0.571, which is negative, actually. Negative. Point 0.021. Right? 0.55 minus 0.571, right? Yeah, okay. So it is negative. Now, some people ignore the negative. But to be honest, it should be there. It just indicates that your estimate was smaller than the actual value as opposed to bigger than the actual value. Okay, makes sense so far? I hope.
Yes.
Okay. Methods of sampling. Yeah, I'm not gonna do this one. Ooh. Oh, I remember this one. Oh, yeah, I remember this one. This one. Oh, okay, what the hell? So the 100 rectangles on the next page are numbered 1 through 100. So there are 100 rectangles here. Okay, some rectangles are squares, some rectangles are not squares, but they're all rectangles. There's 100 of them. Each one is labeled. For example, rectangle number 40 has an area of 8 square units. So let's find rectangle number 40. Here it is, right at the top. Rectangle number 40, 1, 2, 3, 4, 5, 6, 7, 8, 4 by 2. Okay. Your goal is to estimate the average area of all 100 rectangles using a sample of size 5. Now there's 100 rectangles there, and I want you to do a sample of size 5. So what I want everyone to do right now is at random, even though it's not truly at random, write down 5 numbers between 1 to 100. Everyone write down 5 numbers between 1 to 100 on your paper. Try to do it at random. Although the human mind is not capable of truly picking 5 rectangles at random. Does everyone have their 5 numbers? Everyone? Okay, hopefully everyone does. Just pick 5 numbers. And now what I want you to do is find those 5 numbers here. And average those 5 rectangles that you picked to find the average area of your 5 rectangles. And we really need everyone to do this. Everyone have their numbers? Or is anyone still?
Yeah, I'm looking through these.
They are in order, by the way. They go sideways. So 1, 2, 3, 4, 5. So they kind of, you can find your number going this way. We are adding the number of squares in our rectangles and dividing by 5 because we want the average. So we're taking the 5 rectangles that we picked and averaging how many squares there are in them. Does that make sense what I'm saying?
Yes, it does.
Okay.
Wait, so each number has like in that number, we count the amount of squares it has and then we average that out.
Yeah. Mhm.
Okay, so-
That's exactly it. Finished. Everyone else finished? Okay, so let's see if we can figure out how do we do this. Okay, so somebody else down the line. Did anyone get an average of 1, 2? Okay, it's gonna be too slow. Somebody give me an average.
I got 5.4.
Okay, 5.4. Anyone else get 5.4? Alejandro also got 5.4. And then we got 5. After give me all the values, just type them all out. I'll just copy them. So I'll just make a little, actually, I'll do it this way. Everyone, please write them all out. Would be great. And then I will go here. Okay, so what do we have? The first one on the list is, I have a 5 from Sabina. I have 5. Alejandro was 5.4. 6. 9.4. 6.2. 6.4. This didn't work out the way I'd hoped. 8. 10.6. 10.8. 8.4. 7.6. 8.4 by here, 7.6 about here. Okay, so let's suppose 4.8 we got down here. Okay, so it looks like for the most part, everyone, okay, there's more coming, 5.4. Thank you for, okay. So what would you say the average is based upon this well, let's take a step back. Did everyone get the same answer for their sample?
No.
No, obviously not. In fact, for the most part, everyone got different ones. 1 repeat. So not only is there a true value, of course. But one, we don't know the true value. And two, every one of our samples, for the most part, was not equal to the true value, and were not equal to each other. The samples are going to be the sample values themselves are going to have some variance. So not only is how do I want to say this better? I'm sorry, I'm floundering for words here. Even if the true value of the population is given and we know it, our samples are not always going to be equal to that, and our samples are going to have their own distribution. Different samples are going to give you different values. So somehow, even knowing that every sample is going to give a different value, we still somehow want to use our sample to infer something about the population. And that seems a little bit suspect. We see here that every sample is different. What makes me allowed to use my sample to infer something about the population if your sample is going to give you a completely different inference? Every person's sample is a different value. We would all disagree on the true value, but no, we wouldn't disagree. We would just have different estimates, and that's perfectly fine. We all have different estimates of the true value. We all have our sample errors. That's just the way life goes. That I can still use my sample to infer something. I just have to recognize that there's always going to be a little uncertainty between my sample and the true value. This was my approximation, but I get it. It's only an approximation. Everyone's approximation is going to be different. The idea of sampling is not that this is the answer. The idea of sampling is, this is my answer. I'm pretty confident it's somewhere in the vicinity of the true answer, even if it's not exactly equal. So I can still make predictions. In fact, if you go online or you've seen polls, accurate polls don't just tell you the numbers. They don't just say something like, 40% of people want to do this, or 55% of people want to legalize marijuana, or this or that. What do good polls always have after the approximation? If it's a good poll, what should it have out there in the world? What do you see polls have? Well, the sample size might be included, but usually not. Usually the sample size is not what's included. Usually what's included is plus or minus. 55% plus or minus 2% say this. They'll give you a range of values for which they acknowledge that we don't really know the true value. It's somewhere between here and here. 55% plus or minus 2%, somewhere between 53 and 57. Because the samples come with their own uncertainties. Does that make sense? Yes, no, maybe so?
Yeah.
Okay. So the distribution below shows the area of all 100 rectangles. So lots of them are ones, a couple twos, some threes, a lot of fours, a bunch of fives, a sixes, no sevens, and so on. How are you going to have a rectangle of area size 7? Right? It's got to be a, non-prime. Well, I guess you could have 1 by 7, but there aren't any of that. Okay, so this is the actual distribution. There's going to be 100 dots here because there's 100 rectangles. And how would I compute the mean of those 100? How would I compute the mean of those 100?
Wouldn't you add up all the areas and then divide by how many rectangles?
That's certainly one way of doing it. That's the mathematical way of doing it. Don't forget, we also have the balance point approach. We also have the leveling out approach, the redistribution of wealth approach, right? We have various ideas for calculating the average, the mean, right? Yes, no, maybe so?
Yes.
I hope so. Okay, and then we also have the standard deviation. Standard deviation is we had a formula for it, but it's a measure of spread. So the center is 7.4 with a standard deviation of 5.2. Fine. Now, it talks about different methods of sampling. I'm not going to focus on methods of sampling other than the good ones and the bad ones. A good method of sampling is completely random. When you guys picked your 5 numbers for this thing, how did you pick your 5 numbers? What do you do in your head to pick 5 numbers at random? I'm going to take a guess. And I want you to tell me just in chat whether you did something like this or not. Picked one number between 1 and 20, one between 20 and 40, one between 40 and 60, one between 60 and 80, one between 80 and 100. Anyone do it that way, essentially? Just picked one number in this part, in each one there. Did anyone do that? Oh, that's great. What did you guys do to pick 5 numbers at random?
Just think of random numbers that pop into your head.
Did you pick 2 that are next to each other?
No.
Did anyone pick 2 numbers next to each other? If it was truly random, truly random, is it possible that you might have picked 2 numbers next to each other? Right? Think about it. Imagine you did the most random way of doing it. You put 100 numbers down on papers. You put the papers into a hat. You swirled it around. You reached in and you grabbed 5. Could you have ended up with 5 numbers, one after the other? Is that possible?
Yeah.
So a true random way of picking numbers would have had the possibility of 5 numbers in succession. If when you picked 5 random numbers, you made sure not to do that, you made sure not to pick 2 numbers next to each other, then it wasn't really random. Does that make sense? So even if you're blanking and picking random numbers, you're not really picking random numbers because you're making certain that 2 numbers or 3 next to each other are not going to be picked, which means you have some structure to what you did. That's not truly random. Okay, a random number generator, a computer that picks numbers at random, numbers in a hat, that's true randomness. If you're not doing something like that, it's not truly random. And there's, you can have a PhD thesis written on how to pick a random sample. There's so many different types of sampling. There's stratified sampling, where you break the population into groups and pick a sample from each group, maybe 50 states, and you pick a little bit from each state. There's cluster sampling, where you divide it into little pieces and then pick some of those pieces. So imagine dividing it to 50 pieces and picking a little from each piece. That's stratified sampling. 50 pieces and taking a few of those pieces, that's cluster sampling. There's convenience sampling, the very worst kind, convenience sampling. Going in front of the CSUN library with a little clipboard and stopping people at random and asking them questions. That's a horrible way to sample because you're picking who you want. You're like, oh, that person looks like they might talk to me, and that person looks like they're not in a hurry, and this person looks like they might say this and whatever. So you're doing it out of convenience. Oh, it's easy to do it this way. There's what's it called? Voluntary response sampling. That's like a poll online. You're browsing the internet and there's a poll that says, who's your favorite Game of Thrones character? This one, or this one. What do you do when you come across a poll like that online? What do most of you do if you're online and you come across a poll? You skip it usually, unless what? When do you not skip a poll? When do you not keep scrolling? When do you actually answer the poll? When you like it, when you care about the subject, exactly. When it interests you, that's exactly the idea. Voluntary response samples are so bad because the people who respond are people who really care about it. It's not really representative of the entire population. The best type of sample is random sampling. When you truly random and there's no rhyme or reason behind it, it's just random. If it's not that, it's always suspect. I'm not saying it's always horrible. There are times when you want to do it that way, but voluntary response, those are the worst. There's systematic sampling. Go back to the CSUN library example. Don't pick every person who interests you. Pick every fifth person that goes through those doors. 1, 2, 3, 4, stop. You. 1, 2, 3, 4, you. 1, 2, 3, 4, you, and so on. A systematic sampling is actually not a horrible way to sample. It's not as good as random sampling, but it's still pretty good. So there's lots of ways to sample. The most important, of course, being straight up random sampling, which is what we'll talk about right now. Selecting a sample at random from the population is the best method of sampling. It does not mean that every random sample will be representative of the population, but it does mean on the average, if I take all of my samples and I average them, that should be equal to the true value. If you remember back to the 100 rectangle example, we had all these different values. I didn't really stop and guess where the estimate was, but does it seem reasonable looking back on it? I mean, I already erased it, so I don't know the numbers, but there were lots of numbers here, right? Numbers were here, kind of spread out. This was the area where the numbers were, I believe, right? I think 4.8 was the smallest, a bunch of here, some up to here. So does it seem reasonable that 7.4 was the actual average based upon what our sample averages were? Does that seem reasonable?
Yeah.
Sure, because the average of your samples should be the true average. The average of your samples should be the true average. So, okay, this is funny, but let's move on. Okay. Random sampling is a topic first introduced in grade 7 in the California Common Core. Understand that statistics can be used to gain information about a population by examining a sample of the population. Generalizations about a population from a sample are valid only if the sample is representative of the population. Random sampling tends to produce representative samples and therefore supports valid inferences. If it's not representative, you can't infer from it. It might be biased. It might have other things wrong with it. Samples need to be representative. Random sampling tends to do that. So what exactly is random sampling? If I take a sample of size 5 from 100, like our example earlier, every group of 5 rectangles has an equal chance of being chosen. So nobody picked 5 rectangles next to each other, 5 numbers next to each other. But if it's truly random sampling, any 5 were as equally likely to be picked as any other 5, even 5 that were next to each other. Each group of n people has an equal chance of being the sample. So what are some ways of getting a random sample? Names on cards, shuffle and draw, or names in a hat, shuffle and draw. Again, it can list every number, like year 1, year 2, year 3, year 4 for the entire population, and then pick a random digit table or generator, choose numbers. These are ways of getting random samples. Make sense so far?
Yeah.
Okay, so when you take a random sample, you're going to compute what is called a statistic. Parameters are for the population. Those are the true values, whether I know them or I don't know them. Statistics, on the other hand, statistics are what you get from your sample. Your sample average, that's a statistic. The true average, that is a parameter. I want to use my statistic as an approximation for my parameter. So my sample mean, statistic. The actual mean, parameter. So when you take a random sample and compute a statistic, such as the mean, the statistic varies depending on what sample you got. We saw that in the case of the rectangles. We all got different values except for two people who had the same, but for the most part, they're going to be different. If I actually make a dot plot of all of my samples, I see that my dot plot will have an average and my dot plot will have a variance or standard deviation. And in fact, it'll have a size. So let me show you this. Stop sharing for a second so I can generate this. Hold on. Have I ever shown you the central limit theorem applet? Have we ever looked at that?
I don't think so.
Okay, so let me go back here and give you. Okay, can you all see this here?
Yeah.
Have we ever, so we've never seen this in class? I've never shown you this before?
I actually,
You have
I
like,
think we have.
I have,
Yeah.
okay. So sometimes when I show it's, I'm stressing a different idea. So let's just take a look again. If you pick a random looking distribution, what this means is we took 31,744 samples. And the average was 0 this many times, was 1 this many times, was 2 this many times, and so on. And this is the shape of the distribution. And if I change the sample size, my shape changes. But in each case, the distribution will have, it'll have values that vary. I can get different values. And I'll have my average of my shape, and I'll have my standard deviation, which in this case, 24.3 and 12.4. And if I do this, it's now still 21.4.4, and the deviation got smaller. And if I do it like this, it's going to be roughly the same mean. Deviation got smaller again. One of the main ideas of statistics is as the sample size increases, it should hone in on the true value, which means all of my averages should be really, really close, which means the spread should really, really shrink. And it should be really peaked at the true value. That's the idea. So in this case, we have this weird looking distribution. This is what I got. And every one of these is a sample of size 5. And these are my averages. What is the largest estimate from my sample? Well, the largest estimate looks like it's 16, right? This dot over here, correct?
Yeah.
And what's the smallest estimate?
it's by 1, but it's
Let's
Is
see.
it 1
It's,
and a half?
well, this is one, I don't know, maybe 1.4, maybe, give or take. Doesn't really matter the actual number, but certainly somewhere in that vicinity, correct?
Yes.
So if the actual average was 7.4, if the actual average was 7.4, which certainly seems reasonable, what was the largest sample error? What was the largest sample error? Anyone?
it looks like 7.
Well, remember the sample error is actual value minus parameter. The highest actual value was 16. The value was 7.4. So 16 minus 7.4 is what, 8.6?
Yes.
Agreed?
Yeah.
Yeah.
Where is the sampling distribution centered approximately?
Like
It's-
7.
Yeah, I mean, ideally about 7.4, which is the true value, right?
Right.
Ideally. It's clear. I'll skip this, skip this. So, grade 7. Use data from a random sample to draw inferences about a population with an unknown characteristic of interest. Generate multiple samples of the same size to gauge the variation in estimates or predictions. So, sometimes we have a knowledge of the true value, like the Skittles example, 20%. Sometimes we don't have knowledge of the true value. So for example, let's say my students didn't know that there should be 20% red Skittles. So I might have all my students go out and buy Skittles, and remember this is for science, so you should save them and give them to me at the end so I can record them for the next semester and keep them. But if everyone got 40 Skittles and made a dot plot for what percentage of them were reds. So suppose you got a dot plot that looked like this. Suppose this was the actual result from an activity. What would you say based upon this distribution is the true percentage of all red Skittles in existence? What would you say? Anyone? What would you say? Okay, well, look at this graph. Where would the center be?
At 0.22.
Right here. This is your guess. I'm not saying you're wrong. I mean, let's take a look. Here's the highest, so certainly the mode. These seem pretty symmetric across from it. These are symmetric across from that. This one's higher than this, but this one's higher than that, and this one's certainly higher than that. Yeah, I would say about 0.2 seems like a nice balance. If you built this wooden structure and you look for the balance point, I would think about 0.2. So the sample distribution seems to be centered right around where the actual true value should be. And that should be the case. If your samples, if you have enough samples, you should have enough enough dots to construct a dot plot with some reliability for where the true value is located. And that true value should be where the true value is. Does that make sense? I hope it makes sense. Well, actually, we'll start here next time. I see it's already 3:15, so we'll stop here. But we'll finish this next time. Yeah, make sure you go out and get those Skittles. Not Skittles, sorry, orange creamsicles and Skittles. Not at the same time, though. That would just be weird. But you certainly should get orange creamsicle. Just